I hope you all remember what I said yesterday about helping young people become scientists. Okay. Well, of course, I have to begin today by finishing the second lecture. You know, there's a basic rule that no matter how many times you remind yourself that you're trying to do too much material, you're trying to do too much material. Let me finish first talking about random KSAT, and then I'll talk about the stochastic block model of networks and inference in planted systems. So just to recap what we said yesterday, so I'm going to make a random KSAT formula with n variables and m clauses, and each clause, you know, has a bunch of variables, k of them, which are chosen uniformly from all possible k tuples. As Julio said, we don't really care whether or not there are self-interactions, whether we choose the same thing, whether we're allowed to choose the same variable twice. And then we flip each one with probability 1/2. And then we ask, when does this have a satisfying assignment? And as a function of this density alpha, there is a critical value of the density at which these random formulas in the limit that n goes to infinity go from almost always having a satisfying assignment, or being satisfiable, as we say, to almost never being satisfiable. And yesterday I gave you a couple of rigorous bounds on this, and basically it turns out that so I gave you the so-called annealed bound, or what other people call the first moment bound, where the expected number of satisfying assignments becomes exponentially small. That happens when k is large, actually just slightly above the true threshold. And so it turns out that the true threshold is indeed 2 to the k log 2 minus a constant when k is large. Okay? But there's a lot more happening between here and here, and that's what I'm going to sketch today that I meant to sketch yesterday. So first of all, I want to know, recall that our lower bound here, using the second moment method, worked by analyzing the expectation and the second moment, the expectation of the square of the number of satisfying assignments, which is essentially also bounding the variance. Now, that's a lovely probabilistic proof, and it does show that when the expectation is large but the variance is small, there probably is at least one solution. In answer to a question that one of you asked after the lecture, while the kind of standard second moment method doesn't quite get all the way up to the threshold, there are much fancier versions of the second moment method where you apply it not to simply the number of satisfying assignments, but the number of satisfying assignments conditioned on a bunch of things that force them to be typical in some sense. So I won't go into that further. But in any case, that second moment method is what mathematicians call a non-constructive proof. It proves that a solution probably exists, but it gives us no information at all about how to find it. It has no algorithmic content. So what I want to start out today is actually an older result, which dates back to like 1990 or something, when computer scientists were first playing around with these random formulas. And I want to analyze an algorithm, a very, very simple search algorithm, and show that up to a certain density, it works. It succeeds in finding an assignment. Okay? And so let me just toss this out at you. It's kind of cute. So this algorithm is going to be almost the stupidest algorithm imaginable. Okay? So let me first remind you what happens when we set a variable. Okay? So suppose I have this clause, and I have a bunch of other clauses. Okay? Now, suppose that you decide to set the variable x3 true. Well, then this entire clause is happy and essentially disappears from the formula. On the other hand, if I decide to set this variable in the way that the clause doesn't like and set it false, well, this 3-sat clause now becomes a 2-sat clause because it must be satisfied by one of the remaining variables. Okay? If I were then to set x5 true, which is not what this clause was hoping for, now the only way to satisfy it is to set x7 true. It becomes a 1-sat clause, or people often call it a unit clause. And finally, if I then, for some other reason, trying to satisfy something else, if I set x7 false, this becomes an empty clause. It's an existentialist clause. I want to be satisfied, but there's nothing that will satisfy me. So it just cries out in the darkness. Okay. Now, what would normally happen at this point is you would say, oops, we have a contradiction. I need to backtrack and go back to my most recent choice and, for instance, set x7 true instead of false. And in so doing, explore this branching search tree of possible assignments. Okay? And that's sort of the intuitive search algorithm that you would use if you were going to try to figure out if there's a solution or not. Our algorithm is just going to give up at this point. It's not going to backtrack at all. It's going to say, oh, well, I failed. Maybe if you start me over again and I make different random choices, I'll succeed next time. Okay. So our algorithm is going to just charge ahead. It's going to take linear time, except for bookkeeping, which I will ignore. And so at each step, it will permanently set a variable in some way. Okay? And if it creates one of these empty clauses, it says, oh, well, too bad, sorry. Now, so it is going to make one concession to intelligence, which is that if there is a unit clause out there, a clause with only one variable left, it will try to satisfy that. Okay? So at each step, it's going to do this. If there is a unit clause somewhere in the formula, if there's more than one unit clause, for instance, then it will choose one randomly and satisfy it by setting that one variable the way that that unit clause wants. This might create other unit clauses. There might be another unit clause hoping for the opposite. That would be too bad. Oh, well. Now, if there are no unit clauses, choose, by the way, when I say randomly, if you're a mathematician, I mean uniformly at random. Okay. A mathematician would always say, well, randomly according to what probability distribution? Okay, I mean uniformly. Okay. If there are currently no unit clauses, choose from all of the remaining unset variables randomly and flip a coin and simply set that variable to true or false with equal probability. Okay. So this is about the silliest algorithm you can imagine. It does not attempt to look ahead. It does not backtrack if it makes a mistake. But it will turn out to work up to a certain point. OK, so everybody understand the algorithm? So now what we're going to do is yes?
If you have unit clause, then why is it important that we choose it randomly?
If you have multiple unit clauses, well, actually, it won't matter. You could choose the first one in order. I don't know. When you do, I actually don't think that will be necessary to the analysis. Sometimes, for the kind of analysis I'm about to do, it's convenient to say, to choose uniformly
Because
random.
we want to finish all unit clauses at first, right? And then go to other clauses.
Well, so, I mean, yeah, the idea is that there are these dangerous things, unit clauses, that are almost contradictions. They're almost empty clauses. So we better give them priority and satisfy them. Now, like I said, if you have this unit clause and somewhere else in the formula, because some other clause got shortened, you have that unit clause, now you're really stuck. Yeah? Well, okay, but you'll see in a moment that okay, never mind. I mean, you have a contradiction in either case here. Yeah, right. In this case. Right, yes. Or and are both commutative. Yeah. Okay, good. So we're going to analyze this algorithm with a system of differential equations. Yes?
So when you have multi-clause, you flip a coin, and if that gives you contradictory answer, do you give up or you just choose other one?
If there are no unit clauses?
So if you have a bunch of unit clauses, you already have some variables set, and then now you have a multi-clause, then you flip a coin, right?
If you have multiple unit clauses, wait, sorry? I mean, if you have, I mean, if there are any unit clauses, choose one and satisfy that one by setting it the way it wants its variable to be set. Okay? So, like I said, the one thing that this algorithm won't do is, I mean, if there's a brick wall right ahead of it, it will not run into it. Okay? So if there is a unit clause that wants x7 to be true, it will set x7 true, unless it chooses to satisfy some other unit clause instead. Okay?
I think he's asking, like, if you have only multiple clauses and you pick one variable and set it, you get two contradictory.
Sorry, what is by a multiple clause, you mean a clause with more than one variable?
You only have clauses more than one variable, and then you pick one variable and set it, and then you get contradictory unit clauses. Don't do it.
Oh, no, the algorithm doesn't even look ahead that far. Okay, it doesn't even look ahead that far. Okay?
But
Yeah.
you will consider multi-clauses like after, like does it consider multi-clauses at all? Or
Okay, is this what you're referring to? So it could easily happen that one clause wants x3 to be true, and another clause wants x3 to be false. Okay? And it could be that we have, actually this particular situation would be very rare because it corresponds to a small loop. But for instance, if this wants x11 to be true and this wants x11 to be false, let's see. Actually, this would be okay.
so right, but if the first one is x3 and x3 or x3, then x3 must be true, right? And then you go to the second clause, and then you flip the point and say, oh, x3 should be false. And what do you do at this point?
Sorry, what clause do you want me to put here?
x3 and x3.
But inside the clauses we have ors, not ands.
Oh, so the x3 or x3, but
So x3 or x3,
right.
or something else, or not?
That.
Oh, I see. And if somewhere else we have not x3 or not x3, okay, let me point out that this would be very rare in these sparse random formulas. But in any case, yes, the algorithm would flip a coin. And in our analysis, we will actually ignore the event that a variable appears twice in a clause, because that happens with negligible probability. But you're right that in this case, the algorithm would flip a coin, set x3 true or false, and get in trouble either way.
I mean, you can simplify them at first because x3 or x3 is unit clause.
You can also simplify them, but because this is rare, you know, it's rare to choose the same variable twice. if we're only choosing a linear number of variables. Yes, and then the algorithm will fail. So it's okay. Well, but maybe we only got into this situation because we made some previous choices that were bad. Maybe there was another variable here and here that would have fixed this problem. Yes?
So by fail, you mean wipe all of the x's and restart completely?
Well, we're going to analyze sort of one run of the algorithm at a time, and we're going to say that a run of the algorithm fails if it reaches a contradiction, an empty clause. I guess tomorrow I'll be finishing today's lecture. All right. Why?
Why do we consider unit class? Because you have set already the first few variables to be satisfied.
I mean, if I set the variables the wrong way from this clause's point of view, right? I mean, I want Chinese or pizza or Thai. Well, you can't have Chinese. Okay, I want pizza or Thai. You can't have pizza. Okay, I want Thai. You can't have Thai. Wah! Does that make sense? I mean, I know it's not lunchtime yet. I mean, if I set these variables, if I give them the opposite value than the clause wanted, then it shrinks. It has to be satisfied. But am I answering your question, or?
I guess. So you're setting the first few variables to be satisfied. Unsatisfied, sorry.
I'm not setting them. I mean, each of these variables can be true or false. If on this step, okay, let's say that there are currently no unit clauses, I might randomly choose to set x3 false. Now this clause cannot be satisfied by x3. I might then randomly choose to set x5 true, and now this clause can only be satisfied by setting x7 true. Okay. A smarter algorithm would say, gee, a two-variable clause is already more upset, more dangerous than a three-variable clause, so I will give it priority. And indeed, people studied that too, and they get a slightly better result than the one I'm going to show you. But this very simple algorithm, the only thing it does is prioritize unit clauses. And if none of them are currently on the scene, it just makes random choices. Okay. All right, so how are we going to analyze this algorithm? First, I'm going to define S3 as the density of three-variable clauses, or three clauses for short. Okay? Initially, this equals alpha, the density of my formula. And I'm going to define S2 as the density of two-variable clauses. Initially, this is 0. Okay? So what's going to happen is, as I start making random choices, I will satisfy some of these three-variable clauses, but some of them will turn into two-variable clauses, and S2 will increase. If all goes well, I will eventually satisfy everything and make both of these densities go back down to 0. You might ask, well, what about S1? Actually, the number of unit clauses needs never to become extensive. Okay? So I will not write down little s1 for the density of unit clauses, because if I ever get order n of them, there's a really good chance that there are two that contradict each other. Indeed, if you know something called the birthday paradox, even if I have about square root n of them, there starts to be a really good chance that two of them will contradict each other. So I'm first going to analyze these extensive quantities, and then I'm going to deal separately with unit clauses. Okay? Was there a question? Yeah. Well, we're trying to analyze the satisfiability of random formulas with density alpha. Okay?
You define the density as m over n.
Yes, I define the density as m over n. So, which is it's the number. It's the number of 3 clauses divided by the number of variables.
And by variables you mean all n. It doesn't change.
Yeah. Okay. This is the integer number of 3 variable clauses, and yes. Okay. But T will be capital T over n, where T is the number of steps we have done. And since in each step we set one variable of the n variables permanently, this means that the number of variables remaining that are not set yet is 1 minus t times n. So in this step here, when we choose a uniformly random unset variable, we'll be choosing from among these. Okay? Any questions? All right. So, I mean, if this was a mathematics audience, I would first write down a stochastic process on integers and then wave my hands and tell you that when n is large, we can model this stochastic integer process with differential equations. But since this is advertised as a physics audience, I will assume that I can jump directly to the differential equations. But if you want to know, this is all rigorous, and we can bound the fluctuations, et cetera, et cetera. OK. So now let me write down a couple of differential equations that I hope will look OK to you. The first is that ds3 dt, well, let's see. If I set any variable in a 3-variable clause, it ceases to be a 3-variable clause. And there are 3 chances of that for each 3-variable clause, but I'm choosing from among this fraction of unset variables. Now, what about the change in the density of 2-variable clauses? Well, half of these become those, because I set the variable the wrong way in the opinion of that clause. And similarly, if I set either variable in a 2-variable clause, it will cease to be a 2-variable clause, either becoming satisfied or turning into a 1-variable clause. And both of these are easy to solve with those initial conditions. S3 is alpha times 1 minus t cubed, and S2 is 3 halves alpha t 1 minus t squared. OK? Good. Now, but none of this tells us about the real danger, which is the unit clauses proliferating. OK? And like I said, the number of unit clauses is not extensive, so we're going to use a different approach to them. And we're going to use a branching process. And by the way, I'm trying to do this quickly, so I'm using an important fact, which I don't want to sweep under the rug. This algorithm has 2 properties which make this analysis possible. The most important property is that at all points during this algorithm, when it's partway done, the remaining formula is random, conditioned just on those integers, S3 and S2. OK? In other words, if I stopped the process partway through, you would literally know absolutely nothing about the formula, except perhaps, you know, I mean, let's see. Let me be careful here. you would know what variables I had set so far. Okay? But the remaining formula only refers to the variables I haven't set yet. And since the initial formula, all the clauses were chosen by choosing random variables and flipping them half the time, these remaining clauses are still random, with variables flipped half the time. So for instance, if I tell you, yes, there is a unit clause, all you know is that it's one of the unset variables. You have no idea which one, and you have no idea which way it wants to go. Okay? It's only because of that kind of strong randomness that we can use differential equations here. And this is why it's hard to analyze algorithms that go a certain distance and then backtrack and then try something else. Because since you went down there and backtracked, you have now learned a lot about the formula, or in mathematical terms, the probability distribution of the remaining formula is now very complicated. So it's only because we're charging ahead and we never go back that this analysis is rigorous and correct. The other convenient thing is that when I tell you that I'm doing these differential equations, I don't even need to tell you which kind of step I'm doing because of what I just said. A unit clause is a uniformly random unset variable, and it's uniformly random whether it's flipped or not. So when I do this, from the point of view of the rest of the formula, I'm still giving a random variable a random value, just as in this step. So the effect of these two steps on the rest of the formula are the same. There are more complicated algorithms where it would be more complicated, but yes? OK, great. All right. So for the unit clauses, I'm going to use this thing called a branching process. How many of you already know branching processes inside and out? OK, good. So a branching process is something where things have children, as several people in this room have been doing. But these things reproduce asexually. And let's say that at each step, the expected number of children you have is lambda. And in fact, in our case, the number of children will be Poisson distributed with mean lambda when n is large. Although, actually, for some of what I'm going to say, that doesn't really matter. All that matters is that you have lambda children on average. So the most basic question is, if you have lambda children on average, each of your children has lambda children on average, will this entire lineage die out? Or will it, at least with probability bounded above 0, survive to infinity and explode? OK? And as you might imagine, the question is whether lambda is bigger than or less than 1. So if it's less than 1, this is subcritical. And then, for instance, the number of the average number of descendants you will ever have is just this geometric series. Okay? So if you're familiar with the Erdős-Rényi random graph, lambda would be the average number of neighbors, and this would be the expected size of the connected component of the graph to which a vertex belongs. If you don't know about the Erdős-Rényi random graph, go learn about it and ignore what I just said. On the other hand, if lambda is bigger than 1, then this is supercritical. It might happen that you die out. I mean, after all, if the number of children is Poisson distributed, then with probability e to the minus lambda, you have no children. But it's also true that it is infinite with some probability which is bounded above 0. Now, so the question is, what happens to the unit clauses? So unit clauses also reproduce with the help of, they have a life cycle involving the 2-sat clauses. So let's say here I have a unit clause. It wants x3 to be true. But when I do that, over here, I have some 2-sat clause that wants x3 to be false or x8 to be true, well, what happens? I satisfy this unit clause by setting x3 true, but now I've created a new unit clause from this 2-sat clause. So each time you satisfy a unit clause, you generate some new ones, and the expected number you generate, well, it's kind of the same as those terms. You have 2 chances of hitting a 2-sat clause out of all the unset variables. On the other hand, half the time it agrees with the previous unit clause, and it's just satisfied. So we get S2 over 1 minus t, and this is 3/2 times alpha times t times 1 minus t. So what happens as the algorithm proceeds? Is that the number of 3-sat clauses goes down. The number of 2-sat clauses looks like this. And lambda looks like this, t times 1 minus t. The moment of greatest danger is when you've set half the variables, because that's when t times 1 minus t is maximized. At that point, this is 3/8 alpha. Okay? And so, if alpha is less than 8/3 for 3-sat, this branching process remains subcritical throughout the course of the algorithm. And so, to analyze the exact probability of success, you still have to integrate over all the steps of the algorithm, so we have to be a little bit careful. But it turns out that then there's a good chance that the algorithm succeeds in setting all of the variables, dealing with all of the unit clauses, and never creating a contradiction. So we just did 2 things. We proved that for 3-sat, the critical alpha is greater than or equal to 8/3. Okay, 2.667. And recall that for 3-sat, the threshold is about 4.2. So this is not a shameful result. But we did something else besides proving that the formulas are probably satisfiable up to that point. We actually showed that we can find them up to that point, that an algorithm can actually satisfy the formula and find a solution. Okay? Which is, unlike the second moment method, a constructive method of proof, and is presumably also telling us something, it's not clear what yet, about the landscape. Okay? It's telling us in some sense it's not so hard to find a zero-energy ground state back here in physics land. Okay? So we might, we'll talk in a moment about what, if anything, this tells us about the landscape, but at least it means we're not always getting stuck in some other place with a higher energy and failing to satisfy all of the clauses. Now, if you repeat this analysis for k-sat instead of 3-sat, of course it's a little more complicated. You have a system of differential equations because you have clauses of every length from k down to 1, but it's not so hard. And what you get then is that this succeeds up to 2 to the k over k, a factor of k below the actual threshold when k is large. And for a long time, this was the best that we knew algorithms could do. It turns out that there is an analysis of a Monte Carlo algorithm which gets a factor of log k better. Okay? Now, in between here, all the way from 2 to the k over k, or this was revised upward to 2 to the k log k over k, and the actual threshold, for a long time, there was a conjecture that in here, there is no polynomial time algorithm. So if you remember 2 lectures ago, I said that yes, for some NP-complete problems, hard instances are rare and fragile. Here we think that there's a whole range that really take exponential time. And we think they take exponential time because physics. So what is happening to the landscape at this point? So several things happen roughly here in quick succession when k is large, and you've already heard about some of them in the context of more physical glass models. So one of the things that happens is the clustering or dynamical transition, sometimes called dynamical replica symmetry breaking, where essentially the landscape becomes bumpy. Okay? It is not a thermodynamic transition, because if you actually, I know this is sort of all defined at 0 temperature, but bear with me. I mean, if you actually looked at the distribution on all assignments, then these local minima would, well, I mean, the thermodynamics would not be replica symmetry broken. But what happens at this point is that there become many different clusters of solutions of satisfying assignments. There is a typical Hamming distance in between them, which is order n, which, again, that means they disagree on an extensive number of variables. Okay, so these clusters are widely separated from each other. Moreover, there are energy barriers between them of order n. What do I mean by energy barrier? Well, I mean in order to get from a satisfying assignment in this cluster to one in that cluster, if you were doing this with single spin flips, flipping individual variables up and down, you would have to pass through a state where order n of the clauses are unsatisfied. You would have to make a lot of clauses unhappy to get from this cluster to that cluster. Okay. Now, notice that this does not necessarily mean that it is hard to find a solution. Okay? Because you can imagine a search algorithm which just comes and finds one of these clusters, finds a solution, and then you declare victory. And indeed, we know of some problems, such as 3-coloring on random graphs, where we can prove that algorithms not very different from this one do succeed somewhat above this clustering transition. Okay. On the other hand, in physics, we're usually not simply trying to find a solution. We're trying to sample from the set of all solutions. And we believe that that does get hard here, because a Monte Carlo algorithm would have these huge energy barriers to cross. Okay? And so it would take exponential time, even if you did some kind of finite temperature version, where you're willing to unsatisfy a clause with some cost, it would take you exponential time to cross these barriers. Okay. So this dynamical clustering is not actually why we think it becomes hard to even find a solution here. We think that because of something else that happens at not exactly the same density, but pretty close, which is freezing. And I'm carrying out the, I noticed that Florent is paying attention because he knows that there's a 20% chance I'll make a mistake and he'll have to politely correct me here. By the way, I learned all of this stuff from Lenk and Florent. So it's partly their fault if I get it wrong. Only partly. So freezing is a different thing. Freezing is where in each of these clusters there are order n variables which have to be set in a particular way. Okay? So you could imagine, for instance, that in this cluster, all of the solutions x3 is true, and all of the solutions in this cluster x7 is false. And that could be true for half of the variables. Okay? Now, I should say we don't have super good reasons for believing that this makes it hard to find a solution. But the current intuition is that now things are really hard for you, because imagine that you start out with all the variables unset. You're looking at the entire set of possible solutions. Mathematically, that's an n-dimensional hypercube, right? And each solution is a corner of this hypercube. And you're now you're floating in from above, and you're setting different variables, and you're focusing your attention on this slice of the hypercube, that smaller slice, because you're setting more and more variables. So imagine that you've already set enough variables so that you've eliminated all but one cluster. Okay? Now, even among the variables you haven't set yet, there's a lot of variables that you have to get right in this cluster, because all of the solutions in the remaining region that you're searching have, say, x3 true. But you don't know that yet. Okay? That's a complicated logical consequence of the remaining clauses. So now if you set x3 false, you're doomed. But you don't know that yet. So what happens is you set x3 false, you're over here, you've fallen away from the cluster, but you haven't yet derived a contradiction, and you won't do that until you explore another exponentially large search tree on the remaining variables. Okay? Until you realize, that you have to set the frozen variable the way it is frozen in this cluster. Or you have to escape this region entirely and find a different cluster. There are lots of caveats to this picture, okay? And I would say that our belief that it really becomes hard to find a solution above the freezing transition is not a terribly strong belief. One reason it's not terribly strong is of something else that I learned about from Lenka and Guillem that I've been trying to prove so far without success. That there are a small number of clusters above this point that do not have frozen variables. Okay? And if I can get myself into the vicinity of one of those, then maybe I'll be okay. Okay? So there's this thing called the freezing transition, and there's this other thing called the rigidity transition, and one of them is about when most clusters have frozen variables, and the other is where all clusters have frozen variables, and I can't remember which is which, and they can tell me what the current usage in the literature is. I mean, the meaning of these words has fluctuated somewhat over the past 10 years, as they should, as the picture becomes clearer. So it could be that you can actually succeed well above this point. But so far, we do not know of any polynomial time algorithm that succeeds above this point. And indeed, we have a lot of proofs that various classes of algorithms fail. Okay? Keep in mind, if p equals np, then none of these are exponentially hard, but let's not worry about that. Okay? All right. Now, there's another part of the phenomenon here I need to tell you about, and then I will switch to inference and planted models, which is that just a little bit below the satisfiability transition is another phenomenon called condensation. And this is an interesting point at which, so let me tell it to you mathematically first and then physically. At this point, if you were to look at the set of all possible solutions to the random formula, one of these clusters would dominate. And the others, their total size is exponentially smaller than this. When I say 1, I actually mean order 1, or anyway, sub-exponential, but let's say it's 1. Okay? This is the true thermodynamic transition. So before, if I were to look at average quantities averaged over all solutions, I would be averaging over all of these clusters, and I would get nice, smooth results. Here now, if I look at, for instance, the probability in a random solution that x7 is true, I'm looking mostly at this cluster. And now, for instance, if I change to a different formula, a different realization, or even if I add a few more clauses, maybe then destroying this cluster and having this one become the dominant one, now my marginals, or my magnetizations, the probability that a given variable is true or false, fluctuate a lot. And I've been instructed to tell you that this is also the Katzmann transition. Okay? So this is where we have true replica symmetry breaking and a true thermodynamic transition.
What you call dynamical clustering would be in the infinite theory of would be the multi-coupling transition of another sphere. I mean, would be the colloidal glass transition of a colloid of made of glass.
Okay. One N or two? Good. All right.
So in what sense? Is this the Katzmann transition? Does like the entropy of solutions go to 0? Or?
No, there's still exponentially many solutions here. But for instance, we get this kind of chaos in the marginals or in the you know, and like I said, now if you were to look at a thermodynamic quantity, which in this setting is some average over all solutions, you would really be looking at the contribution from one cluster, and which cluster you would be looking at and what its properties are would depend sensitively on the realization, on the choice of random clauses. Okay? All right. So that's all I'm going to say about random KSAT. And I'm now going to switch gears, unless someone forces me to say something else. Yes?
Can you get some insight on the positions of zero-energy solutions by studying non-zero-energy solutions, let's say, satisfying almost all clauses?
You absolutely can. And to put it differently, you can try to work all this out at non-zero temperature. And that apparently is much more complicated, and there are people in this room who can tell you more. In particular, at 0 temperature, we believe we only get one RSB, but I believe at non-zero temperature there's some suggestion we might get full RSB, and you know, things could get even more complicated. But you're right, at non-zero temperature we would be looking not just at clusters of solutions, but at local minima, where if you flip anything, then you decrease the number of satisfied, you increase the number of unsatisfied clauses, and then we would be trying to think about those as well. Okay. All right, good. So let's begin the third lecture. So I'm going to begin the third lecture with an announcement. Where will I write the announcement? I want the announcement to persist for the remainder of my lecture. I am now going to move from the interdisciplinary field of computer science and its interface with statistical physics to the super-duper multi-trans interdisciplinary field of social and biological networks. Woohoo! And as long as I'm going to do that, I should tell you that we have postdocs available. Because if you like this stuff, then you should consider coming and hanging out with us at the Santa Fe Institute. And the deadline is October 30th, which I know is a little unusual for some of you to have the deadline in the fall. So if you or someone you know is about to have a PhD, or if you're in a postdoc and you kind of want another one, then let me know and I can tell you more about the Institute and the fellowship and why you should apply, and I can help you, think about whether or not you want to do that and so on. Okay, great. So, community detection in networks. Okay, so there's some boilerplate I could say here, but lots of people are interested in networks and graphs. I don't think I need to tell you this. And it is a very popular pastime to look for communities in these graphs. And you know, we imagine that in a social network, these are groups of people with similar interests. We imagine that in a protein interaction network or a genetic regulatory network, these are genes or proteins that work together somehow in the cell. That in an ecological network like a food web, they might be organisms that are at a similar trophic level. That means like plants, herbivores, carnivores, and so on. Or they might live in, you know, some part of the habitat, or in any case, they eat each other a lot, and so they're an important functional unit in the food web. So lots of people are interested in community detection for lots of reasons. And so there are hundreds of popular community detection algorithms out there in the world. And most of them, if you don't mind my saying so, including some of my early work, are very ad hoc and offer no theoretical guarantees and, you know, are sort of thrown together just to do a decent job very quickly, okay? And part of the idea here is that people are interested in networks with millions or even billions of nodes, so you do want a very fast algorithm. And even if it's not the most perfect algorithm mathematically, if it's really fast, that is a bonus. On the other hand, in this room, we want mathematically principled algorithms based on ideas from statistical physics. Okay. And it turns out that these algorithms will also be pretty good and pretty fast. But we also want to understand the question of statistical significance, or to put it differently, when are the communities really there? So if I were using slides today, I would show you something where I would show you a network with a couple of hundred nodes where I've colored the nodes red and blue, and I put the red ones here and the blue ones here, and only about 11% of the edges cross from one side to the other, and the other 89% of the edges are within these two groups. And if I showed this to you, you would probably be pretty convinced that I've succeeded in dividing the graph into two communities that are more densely connected within each community than they are between the two communities. And then I say, ha-ha, and I press the space bar on my laptop, and it runs this little animation that took me an afternoon to make in Mathematica. About half of the red nodes slide over here, about half of the blue nodes slide over there, and I get another division of the same graph into two groups with 11% of the edges crossing from one to the other. But you can tell from the colors that these two divisions are totally uncorrelated from each other. And I could show you more, and you might realize that actually these communities are an illusion. And what's happening is that, well, there are roughly 2 to the n ways to divide this graph into communities. So there's some large deviations calculation that you could do. And out of those exponentially many ways to divide it, there are some that look really, really good, even though, now I reveal this, this graph, I generated it by giving everybody 3 edges and wiring these edges up to each other in a completely random way. Okay, so there's no community structure in the underlying process that I used to make the graph. And then I quote a paper of Lenka's with Stefan Böttcher about the fact that, indeed, if you solve this what's called min bisection problem, which is what it sounds like, divided into 2 groups with the smallest possible number of edges, that for a random 3 regular graph in the limit of large n, there are typically solutions about this good. And indeed, many of them that are uncorrelated with each other. So what's happening, of course, is that we're observing local minima in a bumpy landscape. And then I give a little speech about how, in machine learning and statistical inference, people often think that when you fit a model to the data, that you should find the best fit. And they say, of course. What else could one possibly do? And then I say, no, no, no. And I put on my Bayesian hat, and I say, what if the best fit is like here, and its energy is one edge's worth of energy below the others, and meanwhile, there are all these other fits of your model to the data that are almost as good, but which have nothing in common with the fit you found. What you need to understand is not merely the best fit, or the maximum likelihood estimator, or the ground state. You need to understand the entire distribution, in Bayesian terms, the posterior distribution, and in physics terms, the Gibbs distribution, which people in machine learning call the Gibbs distribution. And what you really want to know is that if you sampled from that entire distribution, what, for instance, would be the probability that I belong to the red group or that you belong to the blue group? So what you want to know is really what kind of consensus or agreement do you have between many possible fits of your data to the model. Now, of course, if your posterior distribution is concentrated around the ground state, the most likely thing, then using the maximum likelihood estimator or the maximum a posteriori estimator is okay. But you need to know what the distribution looks like. So not only is finding the best division into two groups NP hard or NP complete, at least for worst case graphs. So not only is that problem hard, but I claim you don't actually care about the answer to that problem anyway. And if you had some other way to compute the statistical properties over the entire distribution, then you would rather do that. Okay, so good. Now, in order to carry out this sort of Bayesian program where we have where we really want to understand the posterior distribution, the downside is that we really have to choose a model. Okay, so and this is where people part ways from the Bayesians. To really be a Bayesian, you have to have an opinion about where the data came from. And many people think that this is just insane and that, come on, you don't really believe in any particular model for where the data, in this case the graph or the network, came from. And they're right about that. And we should worry about that if we're going to deal with real-world networks. Because, of course, real-world networks were not generated by any simple spin-glassy process. Okay? But at least we can say that if we make certain assumptions that where we're dealing with synthetic networks that were generated by some spin-glassy process, we can say very mathematically clear and well-defined things about our ability to find communities in those networks. And then we can try them on real ones, and happily it works pretty well in practice too. Okay. All right. There's the end of the sermon. Now let me start the third lecture. Okay, I'm going to tell you about the stochastic block model. It originated in sociology. It's been rediscovered many times. Some people call it the inhomogeneous random graph. Some people say block model without a space here. But to me, one of the enjoyable differences between English and German is that we don't have these compound words. So so I'm going to put a space. Maybe that fills you with Schadenfreude. Okay. So, all right. So here's the idea. We're going to have K groups. So think of this is going to look very quickly to you like a K-state Potts model. And there's a huge question about how to figure out how many groups a network has. That is a model selection problem, and people argue passionately about how to do it properly. I'm going to assume we know this number. And then each vertex each node I has a label which I will call sigma I, which tells us which group it belongs to. And then two vertices I and j are connected. They belong to the set of edges with probability. I'll call it P sub, I hate double subscripts, but sorry, sigma I comma sigma j. Okay, so there is a little k by k matrix of probabilities that a given vertex from one group is connected to a given vertex of another group. Now, if you're familiar with the Ardish-Rényi graph, it's that. Okay, where every pair is connected with the same probability. This is just the generalization where every pair is connected with a probability which depends only on the groups to which they belong. And now the game that we're going to play, there are many different games we could play, by the way, but the game we're going to focus on is nature chooses these labels uniformly, in which case the k groups are of equal size in expectation. And then nature generates the graph, like this. And then you just get to see the graph. And your job is to find, as well as you can, these labels. Okay. We could also have a game where you get to see some of the labels. We could have a game where you don't get to see the entire graph, where some of the edges are false positives and other links are missing. All sorts of games we could play, and these have relevance in the real world. Because in real-world networks, we do not know all the edges in many cases, and some of the edges are false positives. For instance, just because two proteins stick together in a test tube does not necessarily mean they work together in the cell. Figuring that out is tricky. But let's stick to this simple setting. Now, yes?
Does this give a degree distribution aspect there to show the other one?
It will in a moment, yes. So I'm going to work in the following special case. I'm going to say that if you are in group R and I'm in group S, that first of all, I'm going to say the graph is sparse. So I'm going to scale P down as 1 over n. Can I finish writing the matrix and then? And then I'm going to say that we have, you know, a matrix of constants, CRS, and that CRS is simply something I'll call C in on the diagonal and C out off the diagonal. So the probability you connect to others in your own group is C in over n. To others outside your group is C out over n. Because of this symmetry, this permutation symmetry, and because the groups are of equal size, this also means that the average degree, which I'll call C, and I hope that won't generate confusion, will just be C in over k plus k minus 1 C out, because there are n over k things in each group that you could connect into, and the n's cancel. And as that gentleman just asked, in this sparse case, the degree distribution, the distribution of your coordination number, will be Poisson with mean C. Now, if you know anything about networks, you know, wait a second, no real network has a Poisson degree distribution, and you're right. There are fancier versions of this model where you can have any degree distribution you want. You want a power law, no problem. Okay, but I will focus on this case for simplicity. Did you? Sorry.
Do we know the matrix? We know K, but do we know?
This is another good question. That's called the parameter learning question. So yeah, we could just be given the graph, and we could be trying to find the labels and this matrix of probabilities at the same time. But again, I will assume for simplicity that we do know these probabilities. Yes?
How would you have a non-Poissonian degree distribution? Would you manipulate that with P sigma I, sigma j? Or?
What you would do is you would, rather than independently choosing for each pair whether to connect them or not, you would use what's called the configuration model, where kind of like here, I generated this graph by giving everybody 3 edges and then wiring them randomly. In the same way, you can generate random graphs with any degree distribution you like by first deciding how many edges each vertex has, and then wiring them randomly. Now, that produces random graphs with a desired degree distribution. I would then reweight that probability distribution by the product of these probabilities. And doing this is a little bit tricky, but not that tricky.
Like rich get richer, right? Preferential transfers.
Well, that's a model of growing networks, where at each step a new vertex comes into existence and then connects to the existing ones. So that is one way to get a power law degree distribution. Here we're looking more at, you know, all graphs with a given degree distribution would be equally likely, which is not the case in the preferential attachment model. For instance, in the preferential attachment model, the older vertices typically have larger degree because they've been gathering neighbors for longer. Okay?
You're assuming that all the groups have equal size.
I am assuming that. Or, what is asymptotically the same, I'm assuming that at the beginning of time, everybody had a uniformly random group. We can also modify that assumption by making this distribution non-uniform. Okay?
In your algorithm, you will keep this assumption when you are, finding your.
For the purpose of my remaining time, I will, yes, stick to this special case where we know the entire graph. We know that that a priori the labels are uniform, and where we know this matrix. But all of these things can be relaxed. And I mean, it's the same as saying, for instance, I could add an external field to a spin glass model so that a priori you're not equally likely to be up or down. Okay? So each of the ways that we could relax our assumptions here correspond pretty closely to a way that you might generalize a spin glass model. Okay. Good. I told my family that I was pretty free on Friday, but if you want me to give a couple more lectures, I'd be happy to. All right. So what do we do with this model now in terms of Bayesian inference? So if you aren't a big fan of Bayesian inference, or if you're not sure what that means, don't worry about it, because pretty quickly this is going to turn into physics. So given this model, it's very easy to write down the probability that you would get a particular graph if you had a particular set of labels. Because by definition, this is just the product over all edges in the graph that they exist of the probability that they exist times the product over all the edges that don't exist of the probability that they don't exist. Okay? So, in other words, the sort of forward process of going from a set of labels, a spin configuration on the vertices, to generating the random graph, that process is sort of easy to write down. This is the probability distribution on graphs given the labels. Yes?
So should we be thinking about in the future, be thinking about the configuration as fixed, and then the graphs as the thing we're trying to study?
We're almost there.
Okay.
Right. So there is one true configuration. It is fixed. It is the planted configuration.
Yeah. Right.
But we don't know it. Okay? We're trying to find it.
Okay.
What we're given is the graph. So this is the probability of the graph given the configuration. But what we're interested in is the probability of the configuration given the graph, because we're trying to invert this process. Well, for simplicity, I've chosen all configurations to be equally likely a priori. Normally, in Bayes' rule, I would have to multiply the prior by, I don't even want to do that today. The point is that this is just 1 over z times this. Okay, in other words, it's just this normalized. Z is a partition function. Z, the partition function, is proportional to the total probability that I could get the graph summed or averaged over all planted configurations. Okay, so, I mean, if you want something that looks more like Bayes' rule, this is, now it's really written like Bayes' rule, but I assume that these are all equally likely, so this is just a constant. But, how do we turn this into physics? Well, as you know, we take logarithms, right? Because where do probabilities come from in physics? They come from the Boltzmann distribution, where the probability is e to the minus beta times the energy. Let's set where beta is the inverse temperature, let's set the temperature to 1 so that beta goes away. And then the energy, or let's call it the Hamiltonian, when I take logs and remove a couple of constants, like that factor of n, well, it's the sum over all neighboring pairs, with a minus, of the log of this little coupling, which depends on their states. So if you looked at this thing as a whole, you would say, this is a generalized Potts model, where there is an energy between neighboring pairs, which depends somehow on their states. Note that if Cin is bigger than Cout, this would be a ferromagnetic model, because if you and I are more likely to be connected when they're in the same group, then a Bayesian would say, well, if you are connected, you're more likely to be in the same group. So it's ferromagnetic. In network theory, we also call that assortative or homophilic. We typically in social networks, we assume that people are more likely to hang out with others who are like them, unfortunately. Well, for better or worse, I guess I should say. But there are also networks where disassortative or heterophilic or anti-ferromagnetic community structure is interesting too. For instance, predators eat prey more than they eat other predators, and so on. Okay. Now, there is another term here which I am mostly going to ignore, except when it's convenient for me not to, which is that there is also the effect of the non-edges. Okay? So the fact that you and I are not connected does give us a little bit of information, right? If Florent and I never drank wine together, you would want to know why. Like, did we piss each other off at some point? Why wouldn't we? I know, but if we do, okay, good. So, on the other hand, in a sparse network where the probability of being connected is only order 1 over n, this is not very much information. On the other hand, there are n squared pairs that are not connected. Okay, so in a ferromagnetic model, we cannot ignore this completely because, for instance, if I tell you that people are more likely to be connected if they're in the same group, one thing you could do is say, oh, everyone in the entire network is in the same group. Okay? And then I would say, no, wait, there's also this term, and you need to explain to me why all of these people did not connect very much to all of those people. Okay? So physically what this is would be a model with strong ferromagnetic interactions on the edges and a weak global antiferromagnetic interaction, which basically acts as a kind of external field which makes sure, well, although it depends on sort of the total number of people in each group, it forces us to keep the groups of roughly equal size. Okay? So I will largely ignore that, but if we take logs of this, then of course we'll get n squared terms that are order 1 over n each. Okay. Now, I think in my remaining 15 minutes, I am going to have to restrict myself to telling you the phenomenology of this problem, and then we'll go into the analysis tomorrow. And it will help that we have that picture. Now, I'm going to lay a bit more notation on you for my own convenience. I apologize. I do want to tell you, yeah, here's something I should tell you. I'll tell it to you over here. I want you to think about the effect of a single edge. So imagine that you have a vertex here, I, and that it happens to be in group R, that you somehow knew that, and that you know that it's connected to some vertex J, and suppose this is all you know, okay? And you were trying to figure out, well, given all of the parameters, if this is of type, if this belongs to group R, what's the distribution to which of the group to which J belongs? And you would think about it for a bit, and you would realize that this acts almost like a little step in a Markov chain, or a step in a one-dimensional Ising chain. And you would realize that all you need to do is take this matrix and normalize it to make it stochastic. And then that would be the Markov transition matrix to go from this distribution to that distribution. Does that make sense? I mean, it has to be a stochastic matrix, right? We need a probability distribution. And if you look, you'll see that the average degree is 1 over k times one of those column sums, because C out appears k minus 1 times. And so you would come up with this little matrix, 1 over k times C times C in on the diagonal and C out off the diagonal. And then you would stare at this and say, well, gee, because Chris told me that he was only going to deal with this special case, I can write this even more simply. This is lambda times the identity plus 1 minus lambda times the flat matrix. Capital J is the matrix of all ones today. So this is the completely flat matrix, 1 over k, 1 over k, 1 over k, which turns any probability distribution into the uniform distribution. And where lambda here is just the second eigenvalue of this stochastic matrix, which is C in minus C out over k times C. And then you would look at this and say, oh, but this has a nice interpretation. This says that with probability lambda, I simply copy I's label to J, assuming that they're in the same group. With probability 1 minus lambda, I set J's group label to be uniformly random over the k possible groups, as if this edge were not even there. Okay? So lambda is a kind of, it's a measure of the strength of this model, the strength of the community structure in the network. It's the probability that the existence of an edge essentially forces you to copy the label from one endpoint to the other. Okay? Good. Now that I've defined that, and I will want you to remember lambda tomorrow, so write it down. Now let me tell you some phase transitions in this model. It will turn out, for reasons I will explain tomorrow, that the basic quantity that matters here is the average degree times lambda squared. Why it's lambda squared might be a little mysterious at the moment, because if you imagine a kind of branching process of these edges, and everybody has C neighbors in general, and each of those edges is kind of there with probability lambda and missing with probability 1 minus lambda, you might think, well, sort of this will percolate if C times lambda is bigger than 1. Does that make sense? Does the wrong thing I just said make sense? Okay, good. Well, it turns out mere percolation is not enough. And so it turns out we need C times lambda squared. And I'll try to explain that to you tomorrow. Okay, good. Now once we have this, here's one transition when C times lambda squared is 1. This is the Keston-Stigam transition. It is also known as the D'Almeida-Thouless transition. And it is known also as 6 other things. It is also the tree reconstruction threshold. Anyway, so above this point, it turns out that the problem of finding okay. Let me put this in the following way. I wrote that landscape up there. Okay. So what was wrong in this case? What was wrong here is that there are no real communities because we just have all these little local optima and they have nothing to do with each other. Well, what do we hope happens now that there is a true community structure, a planted state? Well, now what we hope that happens is that that planted state now kind of dominates the landscape. Okay? Meanwhile, over here are a whole lot of other states which have nothing to do with the planted state, and which, if you don't mind, will sort of lump together into a paramagnetic state, an uncorrelated state, a kind of random state. And I'll put those over here. Okay? So now I want you to imagine the inference problem, the problem that you are trying to solve, in the following way. You start at a random state. Maybe you do Monte Carlo. Or you do something else called belief propagation, which somehow made it into the title of all 4 of my lectures, but which I will actually talk about tomorrow. So you're doing Monte Carlo. You start in this sort of at a random initial state. The question is, will you get here? Or even close to here? Above this point, the landscape looks, well, let's see. Above this point, the landscape is really dominated by the planted state. So lots of polynomial time algorithms. We believe Monte Carlo. I mean, we know it in a physics sense. We don't yet know it with a capital K in a math sense. Belief propagation, which I'll discuss, and also spectral algorithms of various kinds. Above this point, this problem is easy. And when I keep saying this problem, what do I mean? I mean finding a state which is correlated with the planted state. So if you define some kind of a magnetization as the correlation with the planted state, all I ask for is non-zero magnetization. I mean, to put that more networky, I want you to label a fraction of the vertices correctly, which is bigger than 1 over k. If you labeled them randomly, you would get 1 over k of them right. I want you to do something better than 1 over k, but I don't mind if you have them switched around, because after all, everything is permutation symmetric here. So if you switch the two groups, that's okay. I could put it yet another way. I want you to produce a labeling where if you think that two nodes are in the same group or different groups, that you're doing better than chance. Okay? So above this point, this is easy. There's another point down here, which is when c times lambda squared is about log k over k. So this point sort of goes down as the number of groups increases. Below this point, this problem is impossible. And I don't mean exponentially hard. I mean impossible. Information theoretically. What could that possibly mean? Well, I like to think of this as nature is trying to communicate with us. But nature only can do this through a certain noisy channel. The planted assignment is the message, but all nature gets to do is make a graph and show us the graph. And the question is, does this channel convey very much information about the message? Okay. And below this point, it doesn't. And this has two consequences which are almost the same, but which are not quite. One is that even if you have all the computational resources in the world, and you have the ability magically to sample from the entire Gibbs distribution on labelings, then you will learn nothing about the planted assignment. Okay. And moreover, thermodynamically speaking, the whole system looks like a random graph, where it really is the Erdős-Rényi graph, where all of these are equal to the same probability, and there are no communities at all. Okay? So in terms of spin glass theory, below this point, the physics of the planted model, where there is a true state with which the couplings, in this case the graph, are correlated, become indistinguishable from the physics of the unplanted model. And in terms of Bayesian inference, it also means that if behind my back I flip a coin, I guess I have to look at the coin. If I flip a coin and then I either make a graph using the stochastic block model with communities, or I make a graph from the Erdős-Rényi model with no communities, you can't tell which I did. At least not with probability tending to 1 as n goes to infinity. Okay? So you can't even reliably tell whether communities exist. And the fact that there is such a phase, I think, struck a lot of people, especially in network theory, as very surprising. You know, I mean, this could happen even when I'm still twice as likely to connect to people in my group as outside my group. And yet, if the graph is sparse, there's just not enough information there to tell what's going on. And if that still doesn't, if you still can't imagine that, I mean, imagine that in this graph, the average degree is only 6. You only have, on average, 6 friends. I don't mean friends, I mean friends. And so even if you knew exactly what groups they belong to, you would still be reasonably uncertain about your own group. Okay? Even if, say, Cn is twice as big as Cout, there would still be some uncertainty. And you can imagine this uncertainty kind of percolating. Okay? So you can imagine a setting where the correlations would decay exponentially with distance. That even if I tell you what group I belong to, okay, now you can do a pretty good job of guessing what groups my neighbors belong to, a slightly better than chance job of guessing what group my neighbors' neighbors belong to, but it dies out, just the way correlations in the Ising model die out above the critical temperature. Okay? Good. In between is a region where we know it is information theoretically possible, but we believe it is exponentially hard. And why do we believe that? Because physics. Because in this regime, it's like the picture I've drawn on the left-hand board. There is a free energy barrier between the paramagnetic state, where, for instance, random initial states would live, and the states around the planted assignment. So in this case, I think the analogy with glasses is quite strong. The point is that if you're doing Monte Carlo, for instance, we believe that it will take exponential time to get from a random initial state into one correlated with the true state, the planted state. So basically, we think no matter what you do, you get stuck there. Okay? The other thing I need to tell you one other thing, two other things, and then I'm really done. This point here is where this landscape goes from this to this. So now, yes, the planted state is still kind of present, but its free energy is greater than that of the paramagnetic state. So it is exponentially suppressed. It does not dominate the thermodynamics of the system. And indeed, there are exponentially many other clusters that look just as good. That's why this here is the same as the condensation transition. So the point at which you can start detecting the planted state, solving the community detection problem, is exactly the point at which, if you will, the macro state correlated with it dominates the thermodynamics, because its free energy is lower than that of the paramagnetic state. Finally, there's a point even below here, which is equivalent to the clustering transition. Below there, we don't even have clusters, and the landscape is smooth. Okay? Good. So in random constraint satisfaction problems, the condensation point has been a source of frustration. It's where it's where fluctuations explode. It's much harder. It's harder to prove bounds above that. The second moment method fails, etc. But where inference is concerned, the condensation point is good news. It's where that single cluster that dominates is the true one, the one that contains the planted state. Let's have lunch.